Okay, start a recording. So in this video, we're going to look at a class MP. So this is a non-deterministic counterpart of the deterministic version, which is P. So because of this non-determinism, it certainly makes problems much more difficult. Okay, so now let's just first look at what this MP is. So remember when we define P, okay, so when we define P, we just use deterministic time, which is P is the union of time, which is deterministic, and to the K, so K from 1 to infinity. So that's deterministic. So MP is defined in the similar way, but using non-deterministic time. So non-deterministic time has the following property. So let me start. Oops. I didn't show up on my screen here. Okay, now I can see it. So non-deterministic time, you start from the initial configuration. Okay, let's just call it Q0. X. And from this initial configuration, you would have more than one choice to go to the next configuration. We'll call it C1, let's C2 maybe, or C11. Okay, this is the first one, right? C12, maybe C1, I1. So this I1 is finite. Okay, so it is finite. And then from here, you also have several other choices until the end. So it's a polynomial time bound. So let's call this as T of n, where n is the length of x, your input. Okay, so there are lots of them. So acceptance notion for non-deterministic Turing machine is that as long as one of these has accept state, you accept it. So that really means that you search for such paths. If you want to say X is not accepted, you have to search for all possible paths, that's exponentially many, to make sure none of them has QA, right? So that is where the difficult points comes in. But nevertheless, if you just define MP, it's just like this. So there is an acceptance path on your input X. That X is accepted. And this path, the length of this path is bounded by your given time bound. So that is what the definition tells us. Okay, so that's what, oops. This is here. Okay. Okay, so what's MP then? So this means that L is in MP means there is a non-deterministic Turing machine M that accepts L in polynomial time. Okay, so once again, in a computation tree of depths, a polynomial depth, right? So you just search for one path to see whether that is a accept path. Okay. So this means that if you are given an input x and p, p is a accepting path for x, then we can verify whether that p is indeed a accepting path in polynomial time, okay? So what I'm trying to say here is that if you are given a p, think of p as a solution to verify this x is accepted, then you verify that p is indeed a accept state is easy to verify. However, we just don't know how to find this p without doing a brute force search for all possible paths. Okay, so that's what I'm trying to say here. And then okay, so we have a second view of this. So we are going to define a notion called a verifier for a language L. So this verifier is a deterministic machine, Turing machine, V. And this L takes input, this should be W here. Okay, so this L takes an input W and a we call that C. So C can be thought of as a witness or a certificate, right? That witness that W is in L, just like the concept we mentioned earlier, that's a path. So you take this and then you simply want to verify this C really is a set path of W. Okay, I use X here. So let me change back to X. The books use W, I like to use X. So let me change that back to X and change this to X. So then I have a second view. So NP is simply the class of languages that have polynomial time verifiers. Okay, so that means if you are given a language, I want to know whether that language is NP, then I just want to see whether I can find a certificate C, and then we verify that certificate C is indeed a solution in polynomial time. Okay, so that makes things easier. So now let's see some example. All right, so satisfiability. So let F be a, so this is the example. Yeah. So let F be a Boolean formula with n variables. Okay, so which means that you got Boolean, you have n Boolean formulas. Okay, let's call it x1, x2, xn. And so you use operations and or conjunction, disjunction, and negation. To connect these things, connect these variables, and you form a Boolean formula. Okay, so then I want to know whether this Boolean formula, let's call them phi or phi, right? I want to know whether this Boolean formula is satisfiable, meaning that whether there is a truth assignment to each variable. So you assign a truth value, which is either true or false, or we can use 0. Normally we use 0 for false and 1 for true. So we find a truth assignment for each variable, and then under that variable, under that truth assignment, we evaluate this Boolean formula to see whether it returns true. So if you want to search for all possible truth assignments, you have 2 to the n many. So that's exponentially many. But if you are presented with a truth assignment, just one truth assignment, and then I evaluate this formula under that truth assignment, so that evaluation is polynomial time. Okay, you simply using the Morgan's law that we know what it is, right? So we simply use the Morgan's law to verify this Boolean formula under a particular truth assignment. So that can be done in linear time, actually, right? So it can be done efficiently. Okay. Hence, we know that satisfiability is in MP because once you present a certificate, I can verify whether that certificate really indeed is really indeed that certificate is a truth assignment, whether that really indeed made this Boolean formula to be true. I can verify that. However, I just don't know how to find one without searching for all possible truth assignments. Okay, so that means that if F is not satisfiable, then of course we have to evaluate this under all truth assignments. Okay, that's exponentially many. So, but nevertheless, satisfiability is in NP. So that's first thing. So you want to make connection to what you learned. We know that in writing code, you're writing conditional statements, you have to include Boolean formulas. So that means that you have to evaluate Boolean formulas. That if it's true, you do this. If it's not true, you do that, right? But in general, given a arbitrary Boolean formula, we want to evaluate it. Whether we want to know whether it's true or not. In general, it's not. It's in NP, okay, and later we'll show that it is actually the hardest problem in NP. Okay, that's NP complete. So that's the first example. Let's look at another example. This is a graph clique problem. So you are given a unidirectional graph, okay? And a clique is a complete graph. So there are two concepts here. So let me start a new whiteboard. Where do I have this? Okay, so we have a concept of complete graph. Complete graph means every pair of nodes, so every pair or every two nodes, okay, are connected. So that's a complete graph. And then inside a graph G, okay, what is it? So this is also called a clique. Okay, so for the given G and for the given K, so K is an integer, we want to know whether G contains a K complete graph, subgraph, K complete subgraph. Okay, So for instance, you have, okay, so this is a clique. This is 3 clique because it has 3 nodes, and then maybe you want to connect the other ones. So let's say this is your G. Then I want to know whether this G contains a 3 clique. Then of course we know it contains 1 here, it is, and then another one here. So it contains 2 clique, and that's it, right? So it contains, at least it contains a 3 clique. All right, so this is in MP. Okay, so in general, you are given a, let's go back to, so clique is a set of instances which has 2 parts. One is the graph, the other one is integer k, and here G is an undirected graph with k clique. Okay, so this is a positive instance. And then we can show that this problem, okay, given a graph, you want to know, given a graph and an integer k, you want to know whether that graph contains a k clique is in MP, because as long as you present it, you are presented with a set of nodes and saying that's a clique, k clique. First you verify whether it has k nodes, and then you verify whether each pair of nodes are connected. If that is true, then this G has a k clique. So the verification is straightforward to verify. However, finding such a clique may not be easy. As a matter of fact, it is also one of the hardest problems in MP. So it is also MP complete. And as a matter of fact, it is even the hardest problem can further be characterized difficulties. This is the most difficult ones. Okay, so the clique problem is very difficult, even though by the surface it doesn't seem that difficult, but it is hard. It's not only just MP complete, it has also other properties that makes it hard. Okay. Let's look at some more example. We just want to get used to this idea. What problems are in MP? So you just need to say, I have an instance, and then I present, I am getting a certificate that claims that it certifies that this instance is positive. Then we just need to verify whether that claim is true or not. So verification is polynomial time. If that is the case, then this problem is in MP. So we try to use example to get used to these ideas. So the next one, we're going to look at the counterpart of clique, which is independent sets. So independent set is just the complement of complete graph. So if a graph is a complete, its complement is independent. So in other words, nodes in this complement have no edges at all. So they are independent. So that's what it means. Okay. So then independent set is also in MP because, again, you simply, so given any G and any K, I just guess, right? I guess a set of nodes and saying that this set of nodes is independent, then verifying whether that set of nodes is indeed independent can be done easily. Okay, so this is, I just checked each pair. So You have k nodes, then you have k choose 2, k choose 2. So my k choose 2 pairs. So my pencil seems to be out of battery. And, let's see. Okay, so that's big O of k squared. So that is the verification time. So it is in MP. Okay, so this part is not too hard. Now, next we're going to see another problem, which is called subset sum. So what you are given is a set of numbers. Okay, call it x1 up to xk. And you are also given another number t. So a set of numbers and a particular integer t, and you want to know whether there is a subset of S such that you add these numbers in that subset up, that's equal to t. Okay, so that is called subset sum. Again, it is in MP because for any instance S and T, if you want to say whether this X and T is a positive instance, you simply guess a subset and then you add them up to see whether it's in T. So guessing is simply, so guessing a solution is equivalent to being given a solution or being given a certificate, then you verify it. So nobody gives it to you, I can make a guess. I guess one, right? So that is also in MP. So this is straightforward. Okay, the last one. Oops. Is a Hamiltonian circuit and Hamiltonian path. Okay, so how can we remove this? I have a hard time to remove this thing, but well. A Hamiltonian circuit is just, so given a graph G, so you have a path that connects all the nodes in G exactly once, and it ends back. So this is a subset of G. So then this is a Hamiltonian circuit. Hamiltonian path means you don't have this. Okay, you start from one node, you go through every other node exactly once and end up at the last node. So that is a Hamiltonian path. Then given a graph G, you want to know whether this graph contains a Hamiltonian circuit. We can simply guess a n edges, right? We guess n edges, and then to see whether these n edges form a cycle that connects all the nodes exactly once. Or if you want to know whether it's a path, I guess n minus 1 edges, and then to see whether these n minus 1 edges form a path that connects all the nodes exactly once. Okay, so this is a proof that this problem is in MP. So we try to get used to this idea how to determine whether the problem is in NP. Now, again, P is a subset of NP, but to prove a problem is in P normally take more effort because you have to indeed come up with a algorithm. Okay, but to prove a problem is in NP, so it would be in general a lot easier because what you need to do is on a given instance, guess a solution and then verify whether that solution actually finishes. This problem is indeed the instance is indeed positive. Okay, so this looks like somebody gives you a solution and then I just want to verify it. Nobody gives it to you, I make a guess, right? So that's equivalent to finding a path in your, that's equivalent to saying that there exists a path in your computation tree that is a set path, okay? So that is how you would tell whether a problem is in NP. Okay, so I'm going to stop the recording.